Okay, so this problem says two charges, Q1 and Q2, both 2 microcoulombs, are placed symmetrically along the x-axis at x equal to plus and minus 3 centimeters. Consider a charge Q3 uh, of 4 microcoulomb and mass 10 milligrams moving along the y-axis. If Q3 starts from a rest at y equal to 2 centimeters, what is its speed when it reaches 4 centimeters? Okay. So what we're going to do is, so here's the x-axis, 0. So this is in centimeters, 3 centimeters minus 3 centimeters. And we are placing Q1 and Q2 here. Here's the y-axis. And Q3 starts here. Okay. And we want to find the velocity of Q3 when it's at 4 centimeters. Okay, so that's what we want to find. Now you guys know that the electrostatic force, so they're all positive charges. Well, let's draw that. Positive, positive, positive charges. So these guys repel him. This guy repels him in that direction. This guy repels him in that direction. The net force is along the y-axis, and Q3 accelerates along the y-axis. Now, the only forces involved are the electrostatic force, which is a conservative force, so mechanical energy should be conserved. Okay, and so that's the principle we'll use. Now, so this is the initial configuration. When Q3 is there, that will be the final configuration. Okay, and so since mechanical energy is conserved, energy in the initial configuration is equal to energy in the final configuration. Okay, kinetic energy initial plus potential energy initial equal to kinetic energy final plus potential energy final. Okay, well, okay, in this problem I should say that these guys are fixed, only this guy is moving. So we are considering his kinetic energy and his potential energy. All the stuff is background. Okay, these guys are fixed. Right, so this guy starts off at rest, so his initial kinetic energy is 0. Okay, and this final kinetic energy is what we are finding. Okay, so now essentially what's happening in this problem is this guy is falling that way. Okay, and just like in gravity, the higher you fall from, the greater your velocity. Okay, so the higher his potential energy, initial potential energy, the greater the greater the potential energy difference, the greater will his velocity be. Okay, so all right, so from this equation, final kinetic energy is initial potential energy minus final potential energy. Okay, so 1/2 mv squared equal to, now we'll write down the potential energies, K E Q1, Q3, R13 initial. Okay, I don't have enough room here, so let me. So initial potential energy is the potential energy of these two guys plus the potential energy of these two guys. This distance. Okay, so the subscript should be Q3 R13 initial plus K Q2 Q3 R23 initial. Okay, so the subscript should be self-explanatory. You guys understand? Minus K Q1 Q3. Okay, I'll draw one distance. This is R13 initial. This is R23 final. Okay, R13 final my plus K Q2 Q3 R23 final. All right, now you guys understand this R13 initial equal to R23 initial and R13 final equal to R23 final. Okay, and since the charges are the same, we'll say Q1 and Q2 are the same. Q1 equal to Q2. Okay, so that'll simplify all expressions. So let's see what happens. So here's what happens: 1/2 mv square. Okay, and okay, let me also calculate R13. Okay, so this is 3 centimeters. This is 2 centimeters. This is 2 centimeters, and that's 4 centimeters. So okay, so this distance is 2 centimeters. This distance is 4 centimeters. So R13 is 3 square plus 2 square, and R23 is 3 square plus 4 square. Okay. So let me calculate those distances first. Yeah. And R13 is 9 plus 4, 13, square root of 13. This is initial, sorry. And R13 final is 3 square plus 4 square, which is 5. R13 final. You guys understand what's going on? Okay. All right. All right. So we'll need all of that. So 1/2 mv square is equal to K Q1 Q3, and R13 is equal to R23, so that's 2 R13 initial minus K Q1 Q3 2 R13 final. Those distances are the same. Okay, so 1/2 mv square equal to K Q1 Q3 1 R13 initial minus 1 . All right, 1/2 mv square equal to 2K. Well, now I guess we can put in the values. Well, V is what we want to find. So this is V is 4K Q1 Q3 divided by M 1 R13 initial to the power half. Okay. All right, now we can start putting in values. Okay, so let's look up the values. Mass is 10 milligrams. The charges are 2 and 4 microcoulombs, and so on. Okay. So all right, so let's put in the values. So this is 4. The Coulomb's constant is 9 times 10 to the 9 Newton meter square by Coulomb square. Q1 is 2 microcoulombs. Q3 is 4 microcoulombs. M is 10 milligrams. Each gram is 10 minus 3 kgs. So this is 10 minus 10 to the power of 6 kgs. A milligram is 10 to the minus 6 kgs. Okay. And then R13 is square root of 13 centimeters and 10 minus 2 meters. 5 into 10 minus 2 meters. The whole thing to the power half. All right. So this is velocity. Okay, let's take care of powers of 10. Okay, so this 1/6 kills that. You're left with plus 3 here. You get a plus 2 to the top, so 5. Plus 5. We don't like plus 5, so we'll spend 1. 10 to the 4 to the power half is 10 square. Okay. All right, so we'll say 10 square meters per second. And let's see, what all do we have left? Oh, well, we killed one of the 10. 10 to the power 5 divided by 10 is 10 to the 4, which is that. Okay, so here's what's left. And I hope I'm right. So 4 times 9 times 2 times 4 is 8. That died. And 1 over square root of 13 minus 1 over 5 to the power half. Okay, so that's what I have left. I'm assuming I'm correct. Okay, so what I get is 472 meters per second. Good. All right, do you guys have any questions on that? So again, what is happening is the following. These guys are fixed. Here's another positive charge, and potential energy is higher here and lower as you go in that direction. So this positive charge would fall in that direction. Okay, and all you're doing is finding its speed when it falls from here to there.